All right. So in the first part, we basically said that when you end up with a function like this and you would like to get its inverse, for example, you have to turn it into the standard form in the table. Things has to be s over s squared plus omega squared, or omega over s squared plus omega squared, or basically s plus a squared, right? And so you do all those math tricks in order to basically be able to eventually bring it in the form that are table friendly. Okay, see s1 over s1 squared plus something, and here is omega over s squared plus omega squared, and then the shift basically turn into e minus t, and all right. So a lot of function basically you can get the Laplace transformation for them, because it's simply just an integration. So that as long as you can do the integration, there is a Laplace transformation. So what does it take to get that integration done? E to minus s of t f of t dt from 0 to infinity.
Continuous function.
No, not really. Even at this piecewise, even piecewise continuous will work too, and we will see a bunch of them, because the input to our system, sometimes it's basically the force, acting on our model would basically be piecewise. You are dropping, someone is coming and dropping something, and then taking the load, elevator or something. So we can actually expect our input function to our system to be piecewise continuous. That's not really a problem. The integration doesn't care. If your f of t is discontinuous like this, or basically piecewise continuous, you split the integration. From 0 to infinity can go from 0 to 5, and then 5 to 7, and 7 to 8. And for each part, f of t change its shape, So from here to here it's something, from here to here it's something else, that's fine. The integration will get split into over those parts. What it takes is that f of t shouldn't blow up the integration, shouldn't make the integration undetermined. So e to minus st should be strong enough to kill the gross of this thing, so that it wouldn't blow up to infinity. Basically saying that f of t should be smaller than e to the power kt. E to the power kt, that's a function that basically can get really, really big, right? It's exponential with time, but he's saying that as long as there is a number k, 7,000, 10,000 multiplied by t, e to minus st will be able to finish it, basically, or keep it in bound. So the point is that as long as the function doesn't grow to infinity, basically, there will be integration, the plus exists. All right? So this is a theoretical part that doesn't really mean anything for us solving the problem. But I'm just telling you that, one, f of t doesn't have to be continuous. Okay? We can split the integration over it. That would be okay. Right. Now, this section, 6.2 now, this is why this is very useful for us, solving ordinary differential equation, because the Laplace of a derivative, so d by dt f of t, that's what we really need to solve ordinary differential equation. Remember, we will end up with dy by dt equal, so we need to the Laplace of this, not Laplace of y, Laplace of dy by dt. Okay, that actually will happen twice in your homework. See this y1 prime plus y2 equals 0, and y1 plus y2 prime. What is this y prime? dy1 by dt. That's what we want to get the Laplace for. So we need the Laplace of the derivative, and it turned out that it's very easy. That's the best part. So it turned out that the differentiation become multiplication by s. So the derivative, Laplace of the derivative of f, is simply, forget about the derivative, just give us f of s and multiply it by s, minus a constant. What is that constant? The initial value of the f of t. See the small f? That's a f of t. F of t at t equals 0, initial value basically. See, when you are solving an ordinary differential equation, you need constant, you need the initial value. y1 of 0, y2 of 0. y1 of 0, y2 of 0. Initially at t equals 0, what were those values are. Right? So those initial value are basically used here. That's f of 0. So whatever this number, if it's 0, you put 0 here. If it's 5, you put 5. The Laplace of the second derivative. In case you have a mass spring system, you will end up with second derivative, not just first derivative. If you have a tank, you're filling it, you get the first order derivative. But if you have a mass and spring system, you will get Newton's second law, mass times acceleration equal the forces. The mass times the acceleration, that's the second derivative of the y. So you get second derivative. Well, the Laplace of the second derivative is simply s squared f of s minus s multiplied by a value, that's the initial value of f of t, minus the initial value of f of prime of t. You know, if you have second order differential equation, you need not just f of 0, you need f of 0 and f of prime of 0. You need two initial conditions, right? So again, those will be numbered, that we will just get them from the initial condition. And in general, it doesn't matter what's the order of the derivative. Even if you have the 10th derivative, it's simply f of n, any derivative. So this n between brackets like this, it doesn't mean n to power f to power n. It means this. It means the nth derivative of f. Okay? As if we need more confusion. But anyway, they decided to call the n derivative basically n between brackets. That's fine. Right. So it's simply s of n, Laplace of f. So Laplace of f. Sorry. You mean capital F of s. Minus s to power n minus 1, the first constant, the f of 0, f of prime of 0, all the way up to the fn minus 1 of 0. And see the s is dropping. So s squared s. So basically, let's call this S7 to be S6, S5, S4, S3, S2, S1. Okay? You got it? I just want you for a second to imagine my life when I was undergraduate taking this without tables. Right? The amount of information that we had to keep in our head. Alright. Which I seem to look more and more to be like my professor when I was a student. He kept telling us, I would like you to imagine that we didn't have calculator when we were students. And they were using the slide rule. I'm like, who cares? We have calculator now. So I guess you guys are right now saying, well, who cares? We have oven book. What do you want from us? So anyway, the differentiation become multiplication. And the integration become division. So if you would like to get the Laplace of the integration, it's the division. And it works the other way too. So when you actually see the Laplace, sorry, you want to get the inverse of 1 over s omega plus s squared omega squared. Then you tell yourself, well, this part, that's going to be my whatever, cosine or sine, right? And then this, all I have to do is integrate the f of t. So you just basically do it by part. You do this, you get the inverse of this, and then you integrate that function. 0 to t dt. Alright? Does this make sense? If you don't believe me, well, we can drive it to ourselves, but you had enough of that. So those has been proven. So for example here, this is an example. He's saying basically that s squared plus omega squared, first we'll think of 1 plus s squared over omega squared. If only we had omega on top of it, right? If only we had omega, but that's okay. We can add omega and divide by omega. So if we have omega, then you look at this, and what is that? Sine omega of t. And the 1 over omega standing outside basically come here. Now you add another s next to it. Do you see that extra s? So the s multiplied by this guy transfer into the integration of sine omega t over omega from 0 to t. This is written d tau. So this is a mistake. This thing here, it should be omega tau, right? Or omega k, omega, but then you're integrating over k. The dummy argument in the integration doesn't matter what you call it, right? The point is you're integrating from 0 to t this function. And so the integration of the sine omega is basically the minus cosine. And then there is another omega. So minus cosine omega t over omega, that's why you get omega square. So that omega square is 1 omega from here, 1 omega from the integration of cosine, omega t. So again, you have to go and remember all the elementary integration things, the cosine, the sine, the e to power at. Okay, remember we had to recall those when we were doing Newton-Raphson. Remember Newton-Raphson, we had to get f and f of prime, and I told you you would need to differentiate those things and try to remember them. So you will also need them if you're going to do something like this. And he's doing it over here too. So s square, how are we going to do this? So first you look here and you say, if only I had my omega, so well, he will end up with this, and then that one extra s will basically turn him into this. And so he basically will look at this thing as 1 over s multiplied by that s square is 1 over s multiplied by everything else. That one, everything else has already been done here. So he will look to this and say that extra s will transfer, or basically will result in this one extra integration, 0 to t, and I'm integrating over tau, kappa, y, basically just turn all the time into tau d tau. You got it? And he do the integration, right? Cosine is sine over omega, and the integration of 1 is, what's the integration of 1? Tau, because we're integrating over tau. So tau, and then you substitute from 0 to t, which will end up being t, correct? Right, so you end up with t like this. Right, of course this tau is written wrong, it actually should be t. So this is t over omega squared sine omega t over omega squared. So he had a problem twice in that book. You got it? So the division, the integration is division, the multiplication, the differentiation become multiplication, and a constant, f of 0. Alright? So this is basically written a little bit nicely, so you can see what's going on. Alright, so here is the moment, the big moment. Finally, we'll have an ordinary differential equation, and we'll see why you have been tortured for the last 1 hour. Now it will pay off. Okay, now we will solve 2 differential equations. Alright, not only 2 simultaneous differential equations, but they could be second order, third order, any. The point is basically you take those differential equations, turn them into the S domain. Now you realize that all those second order, third order, what will happen? The differentiation become multiplication. The second order simply become this second order, the dy d2y by dt squared simply become the s square. S square of y. So when you look to this, is it easy to get y of s? Because it's algebraic equation. All that s, that all the differentiation becoming basically multiplication of s, turn the differential equation into algebraic equation. And so how we can get y of s? Just put y in one side, put everything else on the other side. Well, that's the other side. Okay? So now you have the solution, and the last step is you want to take this with the help of the tables and send them here. So that differential equation has that solution in the t domain. And the 1 over s minus a, that's e to the power t. 1 over s squared minus 1, that's shine t. 1 over s squared, that's t. Where do those come from? Tables. And see how he split? He split them, and each one of them go by itself. But sometimes the trick is to split. Sometimes the trick is to actually be able to split them into parts.
So, yeah, you wrote very easy. I thought that was the easy.
No, the easy part is to get the y of s, but the inverse is not. The price is being paid here. The price is basically to do the Laplace and to do the inverse. And actually, I think it's costly, more costly for us here in the inverse, because taking the Laplace is easier than taking the inverse. We'll see some example. So here is the example that I promised you. Here is the tank, all right? So again, to remind you, there is initial value of the salt in the two tanks. Y1, that's the how many pound of salt inside this tank. Initially it was 0. This guy, initially it has 150 pound per 100 gallon. This tank is 100 gallon, this tank is 100 gallon. And he will start this flow rate at 6 gallon per minute, and the concentration coming in is 1 pound per gallon. Okay? Every gallon coming in has 1 pound per gallon. 1 pound of salt per gallon. So for a free homework problem, okay, at t equal infinity, what would be y2 of 0? Sorry, y2 of infinity.
1 pound.
No. 0, no.
Wouldn't they be the same concentration?
That's correct, but I need the number to get the free homework problem. How much is that number? So Jason is right. The number would be the same in all of them.
75.
Huh?
75 because it'd be equal.
No, not 75.
It's 100.
Who said that? You had one free homework problem. Any problem, past or future, you want to ace it, basically just let me know. He said 100. Why 100? Because the concentration coming in will dominate everywhere, right? At t infinity, the memory of the system will be lost. Whatever will come here will basically be the value everywhere. What's the concentration? 1 pound per gallon. Why? That's why I was asking you a question. Why is how many pound of salt in this tank? So because it's 100 gallon,
It's 100. Yeah.
so you are right that it's 1 gallon, it's 1 pound per gallon. But I asked about the y, and so the whole point behind this is that I want you to make sure that y is not the concentration, it's the mass of salt inside the tanks. That's why y2 of 0 is not 150 per 100. It's not 150 pound per 100 gallon, it's simply 150. Okay? And what was your name? David, good job. So now what we want y1 of t and y2 of t. Let me jump to the solution to show you. The solution would be tank 1 starting from 0, eventually become 100. Tank 2 starting at 150, and you will do something like this and then go to 100. We want this equation. Okay? It's important to find this y of t, y1 of t, and y2 of t. We won't find this. This is the solution that we are after. Okay? So how are you going to get that? So here is the given. The gallon, 100 gallon here, 100 gallon there, 150 pound there, 0 there. This guy have 8 gallon per minute going through. This guy have 2 gallon per minute coming this way. This is the inner loop. So there is an inner loop basically that's circulating 2 gallon between the two tanks. So that 6 coming here together with the 2 recirculating, end up being 8, and then only 6 leaving. Right? So 6 coming in equal to 6 leaving out. So how can I put my hand on those differential equations? And that's not really important for this course. So this course teach you, once you have the differential equation, how do you deal with it? It's the fluid mechanics course that will teach you how to come up with the differential equation that will come from this problem. And it's the system course that will teach you how to come up with the differential equation that will come from a mass spring, bunch of masses, bunch of spring system. So don't worry about this part. But this, if you had a good fluid mechanics professor, he should have explained this for you. All right? Yeah. So when you look to something like this, it's conservation of the concentration. So there is something called the Lewis transport equation, which basically tells us the conservation of any property, whether it's mass, momentum, energy, or the salt mass inside the tank. Right? And it's simply like this. 0 if this material is not being created, there is no source for it. Like a momentum, there is a source for the momentum. It would be the forces. But that concentration, nothing is creating new salt. Unless there is chemical reaction that create this new salt, then we would actually have a source term here. For example, the energy equation, if you remember, from fluid 1, there was Q minus W. Q minus W can create or destroy the energy of the control volume. If there is a turbine that sends the work out to the generator, that is a sink. Anyway, this is a conservation of this mass of the salt. So basically, d by dt, B, that's the concentration per unit mass, multiplied by the mass, plus sigma Bm out minus sigma Bm dot n. This is basically, forget about Reynolds. It's simply saying that mass in minus mass out will end up being what? If I have 10 gallon, 10 pound of salt per minute coming in and only 2 pound of salt per minute leaving, the difference between the 10 and the 2 end up being, and it's the increase, the level basically of the increase, the rate of increase of the salt inside my control volume. That's what it boiled down to, right? But why it's written in that way? Because that is the general form that can be written for any equation: momentum, energy, mass, any property. But you can just simply look at it as basically m dot n, put m dot on the other side. M dot n minus m dot out is simply d by dt of the mass of the salt inside the tank. All right? So when you plug in the number, again, that's not this course, it's someone else's problem. When you put those numbers of the m dot n, the rate coming in, 6, for example, and the rate leaving, 8, I'm doing it for the first tank, so that I can get the concentration in this first tank. The first tank, there is have 6 gallons per minute, there is 2 coming from the second tank, 8 leaving to the second tank. 2 coming, 8 leaving. Alright? So basically there is, when you look to it, there is actually 2 inlet and there is 1 outlet. Okay, 2 inlet, that's why it's minus row 6 minus row 2.
That's a row.
So rho is basically the density pound per gallon. Alright? So in the exam, and in the homework, you start with the differential equation. So don't worry about how did they come up with that differential equation. But basically it's simply this, right? d by dt of the how much salt inside time Bm dot out minus Bm dot n. And it's done for the first tank. You'll end up with that differential equation. And you do it for the second tank now with 2 outlet, 1 inlet. So that's why you get plus, plus, and minus. Right? You will end up with this. Here, we are done with the fluid part. This is the numerical analysis part. So to the differential equation, need to be solved simultaneously because they are basically coupled. y1 and y2 show in each one of them. Right? So how do we solve it in this chapter? Laplace. Let's take the Laplace of the thing. Alright? So, did we ever shoot at the... So, if you do the Laplace of the constant multiplied by y, that's 0.08, right? Multiplied by y1. What's the Laplace of that? Constant multiplied by y, 1 of t. What's the Laplace of point? We want to do the Laplace of the whole equation. We want to take this equation, put it in the S domain. The second equation in the S domain, end up with two equations in the S domain. We'll solve them together, get y1 and y2. So the first step is to take this equation to the S domain, meaning each term need to be turned into the S domain. For example, 6. 6 over S, right? So the 6 becomes 6 over S. 2.02 multiplied by y2. What's the Laplace transformation?
102 over s squared.
Say this again.
0.02 over s squared.
No, this is y of 2. Y2 is just function of time. Y2 of t, f of t, g of t. We call it y2 of t. It's the level, the amount of salt inside the second tank. So what is the Laplace of y2 of t? No, because y is not a constant. Y is function of t. Excellent. Capital Y. Capital Y, right? Capital, meaning y of 2 of t become y2 of s, which I don't know it. We will solve for it, but it's just like what is the Laplace of f of t? Any f of t. What is the Laplace of f of t? Capital F of s, which I don't know it, but you know it's called f of s. So that's why you see this become y2. Okay, y1 just simply become 0.08 y1, capital Y1, right? And now what about dy by dt, dy1 by dt? The differentiation become excellent. S time y1 minus y small y1 of 0. Let's hit the differentiation one more time. The Laplace of the derivative, whether it's f of t or y of t, we call it y prime sometime, like in the homework. Those are y1 prime. That's the dy1 by dt. The Laplace of something like this is simply s f of s minus a constant. That constant is the initial value of that function. So over here, what is the Laplace of dy1 by dt? It will become s y1 of s. Okay, let me write it, because that's what you have to do in the homework actually. dy1 by dt is, can someone help? S y capital Y of s, or actually we can just write y1. It's understood that it's y1 of s, right? Minus small y1 of 0. What's y1 of 0? That's the concentration in the first tank initially. This tank initially y1 of 0 is 0. So this becomes just 0. So simply this term become, this guy here become this guy. And this equation is now this equation. And that's what you will have to do in the homework. You will take the constant become constant over s. You will take y2 and make it capital Y. y1 capital Y1. Derivative s time y minus whatever, minus the constant. And let's do the second equation. Here's the second equation. What is the Laplace of y1? Capital Y1. Laplace of y2, capital Y2 multiplied by that constant. Laplace of y dy2 by dt, sy2 minus y2 of 0, the initial value of y2, which happened to be the 150. The minus and the plus, that's basically because he wants the equation to look like x1 plus x2 equals 7 and x1 minus x2 equals 8. So he put all the constant on one side, the variable on the other side, so that he can see here two equation, two unknown. In the homework, here is the equation, but cosine t. You have to get the Laplace of cosine t. And sine 4t, you have to get the Laplace of sine 4t. Alright? And the initial value, sometimes it's 0, sometimes it's like 3 or 7. That's okay, you just put this value. Alright? So we end up with those two equations. The easy part is actually to solve them together. What's solving them? Meaning you have to tell me y1 is 5s or 5 over s or 5s squared. Just get y1 away from y2. And you can do that, right? By substitution. From the first equation, say what's y1 in terms of y2, put it in this one, you have one equation in y2, get it, substitute back again and get y1. Alright? Not yet. Not yet. So now you can do this just by hand. Right? And so you get y1 and y2, here's y1 and y2. Now the trick is to get the inverse. So you have to split those guys into parts. And so in this case, sometimes it's very easy, sometimes it's not. But basically, you can split them into things that are very table friendly. Something over s, something over s plus 1, something over s squared plus something that works too, right? That can turn into either sine or cosine, depending on do we have s on top or not. And the final step is, well, you look at this, here's y1 of s, let's take the inverse. So obviously 100 over s, when you take the inverse, it's 100. Something over s plus a constant, that's e to minus. Remember, s plus a is e to minus at. So s plus 0.12, that's e to minus 0.12t. Right? And same thing is repeated. And so those are the two solutions for y1 of t and y2 of t. Is that magic? Right? Isn't that pretty? See how we just solve it, basically two algebraic equations. We had two ordained differential equations, and we end up getting the solution by just basically substituting y1 and y2. Right? Right, so that's, you have to basically, you have to learn how to actually do the factorization to turn into basically those things. Right, that will take time, right? But we have to see how does it look like first, so that we can break it into parts. All right. So eventually it turned into 100, and we know the trick. Why? Because it was 1 pound per salt per gallon of water coming in, and so since it's 100 gallon, it has to go to 100 pounds of salt. All right. Questions? Here's another example. This is the second order, okay, and we would like to basically solve it. So again, the integration of something like this is not that easy, right? But with the plus, it's really easy once you just have access to the table. So what's the Laplace? So you basically say the solution is to take the Laplace of this thing, and it will be equal to the Laplace of this thing. Laplace of both sides, basically. So the Laplace of the second derivative is what's the Laplace of the second derivative? S squared f of s minus s f of 0, f of right, minus f prime of 0. And that's why we give you the two initial value. Any time you have a second order, you will have to have two initial value, right? And for y, that's simply y of s. And for t, 1 over s squared from the table, right? So that's what he did over here. Let me clean this out. So he did this over here, right? Here is the second derivative, and here is the y, and the t is 1 over s squared. Now what we should do next? We did the Laplace. What's next? We need y by its. Excellent. That's solving it in the S domain. Just put y in one side, everything else on the other side. So you pull y on one side, okay? In case you are wondering what is the black, why there is black font on top. Well, because last year we were in a room where the projector was like really weak. It wouldn't show up, so I had to basically just write on top of it to make it show up in the. But anyway, you see. All right. So here he is basically just putting y on one side and everything else on the other side, all right? And so it will end up being something like this, all right? So he's talking about transfer function. I will explain this in the next slide in a second. But basically all we are doing is turning y into one side and all the other s's on the other side. Okay? Now what's next? Next is basically to break this into parts so that when we take the inverse, basically it's really easy on us. So this, for example, 1 over s squared minus 1. Well, you can think, well, that s squared I can integrate twice in the t domain, right? But it's actually easier rather than integrating. You don't want to integrate in the t domain. Remember, 1 over s came from integration 0 to t. So rather than integrating it twice, you just basically break this into two brackets, right? And this s plus 1 over s squared minus 1, well, s squared minus 1, that's simply s minus 1 multiplied by s plus 1. So the s minus s plus 1 will cancel, and so that's why this bracket simply just become 1 over s minus 1. Okay? And these two guys basically become here, and you don't believe this, just basically make it with only one denominator, and you will end up with having s squared minus s squared minus 1. So the s squared will cancel s squared, and you will end up just simply with 1. And the final step is, well, here is the three things. Let's take the inverse. 1 over s minus 1, 1 over s squared minus 1, 1 over s squared. So 1 over s minus 1, that's e to the power t. 1 over s squared minus 1, that's sine t. If it was 1 over s squared plus 1, it would have become... No, the plus and the minus turn you from sine to sine. It's the s on top. Turn you from sine to cosine, or from sine to cosine. All right? Very good. So now what is this transfer function? So if you have a system like a mechanical system, springs and masses and stuff, the relation between the input and the output is the transfer function. Well, the relation between them, they have a differential equation relation between the input and the output. It's not simply this over this. But in the S domain, you can turn basically the input on one side, the output on the other side, and you have a bunch of S's multiplied by them. So that would be the transfer function, right? So for example, a spring system, a spring damper mechanism will look, the differential equation for something like this will end up being this: second order, first order, and the function multiplied by the input, where this is the force, for example, acting on the system. All right? So where is the transfer function over here? I could ask you, well, calculate the transfer function for that system. You want to turn them into the S domain so that you basically have the input multiplied by something equal to the output. Alright? So that's the input, the output is y. If you take, those are the initial value, k0 and k1, those are the initial value for y. So if you take the Laplace of this, we did this before. You know the second derivative is s squared minus sy minus y prime. The first order is sy minus y of 0. And b of y is just simply capital By. The input r of t is r of s. Any function of t, whether it's impulse, input, whatever the function is, it just basically become r of s. So now notice that you have a bunch of constants. Those are the initial value. But if you pull the system constant, the a and b in here, time the y, and you put the constant over there and the input over here, now you can now basically realize that this equation, let's take this and put it on the other side. You can get y of s, which is the output, equal to the input r of s multiplied by the transfer function. So the thing that relates the input to the output is the transfer function. The transfer function is also multiplied by the initial value as well, right? So it's basically 1 over the system characteristics. Okay? So now the beauty of something like this is that you basically now, for any input, whether someone is giving you an impulse or giving you a ramp input or a step input, you basically have the solution always in the S domain just simply by multiplying. So that transfer function will not change with different input. It's a function of the system. This rocket, this car, this machine had this transfer function. So you just tell me how you're going to jack it, what is the force you are going to hit it. I just multiply that different input by my transfer function, and here's the solution. It's still in the S domain, but we have the solution somewhere in the S domain, and all it takes now is just take the inverse. Okay? Very good. So I'll stop here. In 6.3 and 6.4 simply we'll just see different kind of input that we can subject the system to. But before you go, I just want to tell you that there is all those tables at the end of the chapter that's really useful when you're solving the homework. Where are they? They're over here. So, right, so 6.8, you find all those things that we talked about that you need to do the inverse and the Laplace. They are written over here, right? And 6.9, all those functions. You would need this when you are solving the homework.